Welcome to Lecture 3 of Physics 506. In this lecture, we're going to be focused primarily on the simple harmonic oscillator. We're going to show you how you get the energy eigenstates, the wave functions, and we're also going to look at uncertainty relations. The approach that we're going to give you here is a little bit different from what you've seen in textbooks, so please pay attention to how we do it here. The simple harmonic oscillator Hamiltonian is given by the sum of the kinetic energy plus the potential energy. That's given by p squared over 2m, p being an operator, plus 1/2 m omega squared, omega 0 squared times x squared, x being an operator. Many textbooks postulate ladder operators as a trick solution to solving the Hamiltonian. Sometimes they won't be so blatant and call it a trick solution. They'll call it a operator-based solution. But really what I'd like you to think about is go back to your high school algebra and think about factorizing a polynomial. We know that the difference of two squares can be factorized as a minus b times a plus b equals a squared minus b squared. If I instead look at a plus ib times a minus ib, I'll get a squared plus b squared. So using that philosophy, we might want to think about, can we factorize this Hamiltonian as an operator? 1 over square root of 2m p hat plus I m omega x hat times 1 over square root of 2m p hat minus I m omega 0 x hat. The first operator we'll call a dagger. The second we'll call a. You might ask, why did I pick them in that order? I could have easily have moved the a operator to the left-hand side and the a dagger to the right-hand side. This question about the ordering of the operators is actually a very important question, one that is almost always neglected in the textbooks that offer this as a trick solution. We're going to be dealing with this a little bit later in the class, and you'll understand exactly why the choice is to put that a dagger operator to the left and the a operator to the right. Now, however, because these are operators, when we work out the product, there's an ordering that has to be taken into account. So the cross terms have an ordering to them that is given by minus I m omega, the commutator of p with x hat, because one of those terms will have a plus I, the other will have a minus I that is multiplying it. The terms that are the direct terms, p with itself and x with itself, well, p commutes with itself and x commutes with itself. So there's no ordering problem there. And those terms just get multiplied together and then added into the summation. Now that commutator can be easily evaluated. The commutator of p with x is just minus I h bar. So that's just a number. We can plug in the numbers and simplify, and we find that a dagger times a is equal to the Hamiltonian I wanted it to equal minus 1/2 h bar omega 0. So that only differs by a constant. I can add 1/2 h bar omega 0 on both sides, and now I have found that the Hamiltonian is given by a dagger a plus 1/2 h bar omega. Now these are capital A's. They're different from the raising and lowering operators that you might be familiar with. We'll get to how you get back to the ones you're more familiar with a little bit later in the lecture. Now, if we recall an energy eigenstate psi, I'm using the Dirac-Bra-Ket notation with a ket psi, and the energy E will equal the expectation value of psi h psi, because h acting on psi will be E times psi because it's an eigenvalue eigenvector relationship. And then if I multiply by psi, because the psi is normalized, Bra-Ket psi psi is equal to 1, and so that net result will equal E when the psi's are normalized. Now, let's just calculate what the energy expectation value would be, psi h psi. Well, it's just equal to psi a dagger a psi plus 1/2 h bar omega 0. This means that our energy is larger than or equal to 1/2 h bar omega 0 because psi a dagger a psi is the norm of the state a operator acting on psi. Be sure you understand that carefully. If I take the vector a operator acting on psi and I take its Hermitian conjugate, I will get psi bra a dagger. Now the norm of any vector in my Hilbert space is a number that is larger than or equal to 0. That means that the energy is minimized if I can find a state that A acting on that state annihilates the state and gives 0, because then the norm of that state is equal to 0, and my energy will be 1/2 h bar omega 0. Now we're using the notation ket with a 0 in it to denote the ground state. The ground state energy is equal to then 1/2 h bar omega 0. And for the moment, we're simply going to assume that such a state exists. Later, we will see exactly why such a state does exist. The next thing we're going to work on is something called an intertwining relation. Again, yes, I know you've never heard of an intertwining relation, but we're going to work it out here, and you're going to understand what it is very quickly. Essentially, what an intertwining relation is it says, let's take a raising operator, a dagger, and move it to the left through the Hamiltonian h. So I'm going to start with h multiplying a dagger. I'm going to write out what h is. Remember, we factorized it. So it's equal to a dagger a plus 1/2 h bar omega. I'm going to bring that a dagger into the parenthesis, and then I'm going to pull an a dagger out to the left-hand side. That leaves me with an a dagger plus 1/2 h bar omega inside the parenthesis. That a dagger I'm going to write as a dagger a plus the commutator of a with a dagger. Why am I doing it that way? Well, a dagger a plus 1/2 h bar omega is just equal to the Hamiltonian h. So that commutator is the difference that I get when I move the a dagger through the Hamiltonian. Well, let's calculate this commutator between a and a dagger. It's 1/2m, the commutator of p hat minus I m omega 0 x hat, with p hat plus I m omega x hat. Now, I can think about foiling out the commutator. Commutator of p with itself is 0. Commutator of x with itself is 0. But I'm left with terms that involve commutator of p with x and commutator of x with p. You can see that they each come in with opposite signs. So if I interchange the order and write everything as the commutator of p with x, I'm going to get a 1/2m and I m omega 0 and a factor of 2 by adding together those two terms. Now, commutator of p with x is just minus I h bar. So in the end, when all the dust settles, I'm going to get h bar omega 0 for that commutator. So we can plug that in. What we've learned is h multiplied by a dagger is the same as a dagger multiplied by h plus h bar omega 0. And the way you can think about this is if I move my a dagger to the left through the Hamiltonian gets shifted by a constant by h bar omega 0. We're going to use this intertwining relation to find all of the energy eigenstates. Here's how we do it. Our claim is that a dagger to the n acting on the ground state is an eigenstate. Let's prove that to you. Well, if it's an eigenstate, then h acting on that state must equal an energy E times that state. So let's act h on that state. Let's write out what a dagger to the n is. Well, it's just a dagger times a dagger to the n minus 1. Now, h a dagger can be written as a dagger times h plus h bar omega 0. And then that's multiplying a dagger to the n minus 1 times the ground state. Now, let me continue and move that through another little n minus 1 times. Every time I move it through, I get another factor of h bar omega 0 that is an additional shift to the Hamiltonian h. So by the time I've moved through all of those n operators, I'll have h plus n times h bar omega 0 acting on the ground state. Now, n h bar omega 0, that's just a number. Okay, so I don't have to worry about anything with that. H acting on the ground state, well, we know what that is. It's 1/2 h bar omega 0 because that's an eigenvalue, eigenvector relationship between h and the ground state vector 0, ket 0. Okay, so that means that I have a number, n plus 1/2 times h bar omega, but numbers commute with operators. So I can move that all the way out to the left, and then I'm going to define En to be n plus 1/2 h bar omega 0. And you see what I've just shown is h acting on a dagger n times the ket 0 is equal to En times a dagger n times the ket 0. And that tells me the energy eigenvalue En is n plus 1/2 times h bar omega 0. Okay? It's that simple. We just got every single eigenstate of the simple harmonic oscillator. Now, we can also use the intertwining relationship to do normalization. Let me show you how that works. Let's look at the normalization of this state that we just found as an energy eigenstate, the state a dagger raised to the nth power acting on the ground state. If I take its Hermitian conjugate as the bra and look at the bra-ket inner product, what I find is I have bra 0, a to the n, a dagger to the n, ket 0. Let's pull out the rightmost factor of a and the leftmost factor of a dagger. They'll meet in the middle, and I'll have an a dagger there. Well, we know what AA dagger is. It's just equal to h plus 1/2 h bar omega 0. We worked that out on the first page. We worked out what A dagger A is, but we also worked out what the commutator of A with A dagger is, and you can use that to verify that AA dagger is equal to h plus 1/2 h bar omega 0. Now, I'm going to use intertwining to move that h through all of those n minus 1 A daggers, and in the end, I'm going to get another n minus 1 h bar omega 0s, and so when all the dust settles, I'll have h plus n minus 1/2 times h bar omega 0 multiplying the ground state. Well, h acting on the ground state is just equal to 1/2 h bar omega 0. So the net is I get a number n times h bar omega 0. And look what I did. I now have to calculate the Brockett sandwich where it has a power of n minus 1 rather than n. Well, I can just repeat this n minus 1 more times. I hope you can see you're going to get an n factorial, and you're going to get an h bar omega 0 raised to the nth power multiplied by the Brockett inner product of the ground state with itself. Now, for the moment, we're going to assume that that ground state is a normalized state, so that Brockett sandwich is going to just equal 1. And what we have found is we can calculate what the norm of A dagger to the n acting on the ground state is, and I can take 1 over the square root of that, multiply it by the state. I'm going to call that state n, and that is my normalized energy eigenstate. So the state n, ket n, is equal to A dagger raised to the nth power divided by, that should be square root of n factorial times h bar omega 0 to the n over 2 acting on the ket 0. That has energy En equals h bar omega 0 times n plus 1/2. So I apologize, there is a typo there. It should be square root of n factorial. I will, of course, correct that for you in the notes. Now, let's get to the conventional Dirac raising and lowering operators. Those are denoted with a little a dagger and a little a, and it's just a renormalization of these operators. Minus I over the square root of h bar omega times big A dagger is equal to little a dagger, and I over square root of h bar omega 0 times big A is equal to little a. I can now take the a and the a dagger and I can re-express them in terms of the x and p operators. We will get square root of m omega 0 over 2h bar x minus I over m omega 0 p, and a is equal to square root of m omega over 2h bar x plus I over m omega 0 p. Now, it's a simple operation to calculate the commutator of a with a dagger. You'll find it's equal to 1. That is very easy to sort through because the factors, it's equal to 1 over h bar omega times the commutator of big A with big A dagger, and we already saw that that commutator was equal to h bar omega 0. So it's very easy to see that the commutator of little a with little a dagger is equal to 1. The Hamiltonian written in this form is h bar omega 0 times little a dagger, little a plus 1/2. The condition for the ground state is little a acting on the ground state is equal to 0, and my excited states n are equal to little a dagger raised to the nth power divided by the square root of n factorial, all acting on the ground state. Now, you notice that I did actually remove a inconsequential phase of minus I to the nth power in order to make this connection to the different states. All right, our next thing that we're going to do is we're going to calculate the wave function. So let's get ready to do that. In order to do that, we need to recall that the eigenstate of position satisfies x operator acting on an eigenstate of position ket x is equal to x number times ket x. I'm using the value of the eigenvalue under the position operator to be the label of the ket that corresponds to the eigenstate. This is a notation that you should be familiar with, but it's very easy to get lost in what is an operator, what is a number, other things like that. So remember, in this class, I will always put hats on the operators, so you will never have any confusion of what is an operator and what is a number. So to be clear, we have an operator acting on a vector on the left-hand side, and it's equal to a number times the vector. That's the standard eigenvector-eigenvalue relationship. Now, our claim is that the state e to the minus I x number p operator divided by h bar acting on the state x equals 0, that is the position eigenstate at the origin of the coordinate system. That is equal to the position eigenvector ket x at location x. Let's prove that. Well, what do? Well, we simply operate the operator x on the state x. I then expand that state x as e to the minus I x p hat over h bar times the state x equals 0. We're now going to use our multiply by 1 trick. I'm going to multiply by e to the minus I x p over h bar and e to the I x p over h bar from the left. And now you can recognize I have a Hadamard there. I have e to the I x p over h bar, x operator, e to the minus I x p operator over h bar. Okay? Well, we can evaluate the Hadamard. I get x operator, that's the first term, plus ix over h bar, commutator of p with x, plus 1/2 ix over h bar squared, double nested commutator of p with the commutator of p with x, and so forth. The sum going all the way out to infinity, everything acting on the state x equals 0. But here it's very nice. The Hadamard, this is one of the truncating Hadamards. So the commutator of p with x is just minus I h bar. So I'm going to get x hat plus x number. And then the commutator of p with a number is just equal to 0. So the second nested commutator and all further commutators after that are all equal to 0, and they'll vanish. Now, let's take that x operator and act it on the state x equals 0. Well, the eigenvalue at the origin is just equal to 0. So x operator acting on the state x equals 0 is equal to 0 times x equals 0, which is just 0. So that term goes away. I'm left with x number acting on the state x equals 0. Well, that's a number. I can pull it out to the left, and then I can use my definition of what the ket x was, and sure enough, you see that x operator acting on state on ket x is equal to x number times ket x. There shouldn't be a hat on that ket on the left-hand side. I'll also remove that in the notes that you get. So it is an eigenfunction. Now we call this operator e to the minus I x p hat over h bar. That's the translation operator. You may or may not have encountered that previously in another class. Now, before we calculate the wave function, it is worthwhile to talk a little bit about what a wave function really is. So the wave function is constructed by the overlap of two eigenfunctions from non-commuting operators. We should not think of this as a physical state that the particle is in between measurements. It is instead a calculational tool used to determine the results of experiments. Oftentimes, conventional quantum mechanics instruction overemphasizes the importance of the wave function in coordinate space. You should not do this. We can interpret the overlap in two different ways. For example, psi n of x defined as the Braket sandwich xn can be thought of as the probability amplitude to find a particle that has energy En in the harmonic oscillator with respect to the harmonic oscillator Hamiltonian to be found in the region near x. We assume the energies are non-degenerate for simplicity here. Of course, in the simple harmonic oscillator, they are non-degenerate. It is similarly the probability amplitude, technically speaking, the complex conjugate of the probability amplitude, to find a particle located near x that has energy En. So you can think of it in this opposite way as the wave function of the position eigenvector in the harmonic oscillator basis. Okay? Now, it's important to note that the modulus squared of these probability amplitudes are, of course, the same, whether I look at the xn Braket sandwich or the nx Braket sandwich. Now, it's easy to overemphasize the importance of psi of x, but we can also find psi of p and other wave functions as well. When we look at this from an operator perspective, as I'm going to be emphasizing in this course, we will see that we can employ translation to relate the amplitude at the origin to the amplitude anywhere else in the wave function. Amazingly, all of these results come simply from the operator algebra and the fact that the commutator of x with p is equal to I h bar. I think you're going to be really amazed when you see this and you see us go through this calculation in just a moment. Now, in particular, we do not need the Schrodinger equation or any other differential equation to tell us how to determine the wave function. You may be shocked by that statement, but I'm going to just show you why that's true. It also follows that from the properties of the ground state and the ladder operators. That's all that you need to get the wave function. Now, this holds not just for the simple harmonic oscillator, which is often the only operator-based system that you deal with in quantum mechanics classes, but we're going to see it holds for all solvable problems later in the class. All right, so with all of that wordiness, let's get ready now to calculate the wave function. So psi n of x is the overlap of bra x with energy eigenstate n. Bra x is just x equals 0 e to the I x p operator over h bar. The sign is changed because I took the Hermitian conjugate. and the energy eigenstate n is little a dagger to the nth power divided by square root of n factorial times ket 0. Now we have to remember that the p operator can be written in terms of the raising and lowering operators as a minus a dagger m omega 0 over 2I times the square root of 2h bar over m omega 0. Or if you simplify that, minus I square root of h bar m omega 0 over 2 times a minus a dagger. Now don't worry if you can't remember this. I can never remember this myself. I always have to look it up. I've done the looking up for you so you don't have to go back and look it up, but don't be worried if you can't remember this relationship between raising and lowering operators and the x or the p operator. This is something that you can always look up when you need it. Okay? Now, that means that the operator, e to the I xp operator over h bar becomes x times the square root of m omega 0 over 2h bar times a minus a dagger. The I has actually disappeared because I have an I times a minus I, and that's actually a real exponent that's in there. So the question is, how do we use these operators to get to the wave function? Now, I have told you about this, but it's a good time to remind you that what do you do when you have a problem that you're trying to solve? Well, first thing to do is to figure out what do I know and how can I use what I know to get to where I need to be. All right, well, we only know two things about the states. We know that the ground state is annihilated by the A operator, and we know that the state x equals 0 is annihilated by the x operator. Now, you might think of it a little bit weird of my saying that the x operator can act as an annihilation operator, but it does for the position eigenstate at the origin. These relationships, these annihilation relationships, are extraordinarily important in quantum mechanics. We always look for finding such annihilation relations. That is how we get our work done, that plus operator identities, and you're going to see how that works. But let me just show you a couple of quick things. So in particular, if A acting on the state on the ground state 0 is equal to 0, then e to the alpha a, where alpha is a number acting on the state 0, is just equal to the state 0, because I can write that as a power series expansion, and only the one term survives. All of the A operator terms, they just annihilate against the state. Similarly, e to the beta x operator acting on the state x equals 0 is just equal to the state x equals 0. And this is for any real numbers, numbers, real or complex, alpha and beta. All right, so now this leads to a potential strategy to simplify the matrix element. We have to convert the e to the alpha p hat into some kind of e to the alpha prime x hat, because then e to the alpha prime x hat, when it acts to the left on the state x equals 0, it goes away. It gets replaced by 1. Now, if we recall that p hat is proportional to a minus a dagger, and x hat is proportional to a plus a dagger, that tells us that we should do the following thing. We should take our e to the some constant alpha times p hat and rewrite that as e to the minus alpha a dagger e to the alpha a times some correction terms. You see, we'll have to use BCH to do that because we're taking two operators in the exponent and rewriting it as the two factors, e to the a times e to the b. Then I'm going to want to take my e to the alpha a and I want to move it to the right using things like the Hadamard lemma until I can get it next to e to the alpha a times the state 0, where it's going to disappear. It will be replaced by the number 1. And then I'm going to reintroduce e to the minus alpha times a times that state, because that operator acting on the state 0 is also just equal to 0. And then I'm going to move that state to the left until I can get it next to the e to the minus alpha a dagger. Then I'm going to use BCH to put both into the same exponent. I'll get something that is proportional to a plus a dagger in the exponent, and of course some correction terms. And then when that operates on the state x equals 0, it's going to get rid of the exponent, because the exponent acting on that state is going to be replaced by 1. This will allow us to get rid of all of the exponential terms. And then we'll need to figure out how we deal with the rest of the expression. And to do that, we're going to similarly use the facts that a hat operator acting on 0 is equal to 0, and x hat acting on x equals 0 is equal to 0. Okay, are you ready? We're going to now go through all of these details carefully. Okay, now I want you to remember that e to the I x p hat over h bar, we already said what this was. It's exponential of x number square root of m omega 0 over 2h bar times a minus a dagger. And I can rewrite that. It's x square root of m omega 0 over 2h bar times minus a dagger plus a. I've written it in that form because I want the a dagger term to be on the left. I'm going to call that a tilde hat, if you like, or just a big A hat. It's not the same as our old big A hat earlier in the lecture, and a big B hat. Now, if we recall the fact that the commutator of A with A dagger is equal to 1, we can now use BCH. BCH was in the form e to the big A, e to the big B was equal to e to the big A plus e to the big B plus 1/2 commutator of A with B. Now, commutator of big A with big B is just a number. So I can pull that out of the exponent, and I can even move it on to the left-hand side. So we get e to the A plus B operators are equal to e to the A times e to the B times e to the minus 1/2 commutator of A with B. Now here we have A operators minus x square root of m omega 0 over 2h bar A dagger. B is x square root of m omega 0 over 2h bar A. Commutator of A with B will be plus m omega 0 over 2h bar x squared. And when we bring that out, I have to multiply it by a minus 1/2. So I'm going to get psi n of x is x equals 0, e to the minus m omega 0 over 4h bar x squared, square root of n factorial, e to the minus x square root of m omega 0 over 2h bar a hat dagger, e to the x square root of m omega 0 over 2h bar a hat, multiplied, of course, by the a dagger to the n times the ground state ket 0. Now, our next step is to do multiply by 1. I multiply by e to the minus x square root of m omega 0 over 2h bar a hat, e to the x square root of m omega 0 over 2h bar a hat. That is obviously equal to 1. The term e to the x square root of m omega 0 over 2h bar a acting on the state 0, just replace the exponential by 1. It's just equal to 0. The terms in the middle, that is a Hadamard that I have created. I can move the Hadamard inside the power, and now I just evaluate the Hadamard. Because the commutator of A with A dagger is a number, the Hadamard terminates after just one term, so I'll get A dagger plus x square root of m omega 0 over 2h bar inside that power n. All right, you guys with me? If not, just pause the video and take a look again at how we did that. Now, we're going to introduce this factor at the ground state ket, e to the minus x. I just changed the sign of what it was before, e to the minus x square root of m omega 0 over 2h bar times a hat. I'm going to now multiply by 1 in between the a dagger plus x and other stuff raised to the nth power, and that exponential of stuff times the a dagger. I'm going to put it in the right order so that I create a Hadamard again. Because the signs have changed with the Hadamard, this shifts the A again by the same amount. So I now get a total shift that is twice as much. And what we have here is we'll have a e to the minus x square root of m omega over 2h bar a dagger, e to the minus x square root of m omega 0 over 2h bar a hat. And then I'll have my a dagger plus x square root of 2m omega 0 over h bar, whole thing raised to the nth power. All right, we're ready now to do our BCH. We're now doing the BCH to put them into the exponent. Big A is equal to minus x square root of m omega 0 over 2h bar a dagger. Big B is equal to minus x square root of m omega 0 over 2h bar a hat. And using our formula with the commutator, we find that they both go up top. I get the term that has an a plus a dagger, and I get a minus 1/2 m omega 0 over 2h bar x squared. That's the same term. That's just a number, so I can pull it out. That's the same as what I had before. So that Gaussian term in the front gets doubled in the exponent. And now I can replace the exponent, the a plus a dagger, with the x hat. And when that operator acts on x equals 0, it gets replaced by 1. So we have done everything that we had described before. We have gotten it now into this form right here, inside the box. So I've got this term that I have to still evaluate. X equals 0, a dagger plus x square root of 2m omega 0 over h bar raised to the nth power acting on the ket 0. Now, when I have an expression like this that I really know nothing about, I've not seen anything like that before, we got to figure out what the thing is, okay? Let's take a look at some concrete examples. Let's look at n equals 0. Well, n equals 0 is easy. That's just the overlap of x equals 0 with the ground state ket 0, and that is just a number. That is the wave function at x equals 0. That's just a number. I can think of it as the normalization constant. In fact, we're going to be using that as the normalization constant. Okay, let's look at n equals 1. For n equals 1, I'm going to get a dagger plus x square root of 2m omega 0 over h bar. Now look, that a dagger is acting on the x equals 0. But remember, x acting on x equals 0 is equal to 0, and x is proportional to a plus a dagger. So I can take that a dagger, I can use an add 0 trick and write it as a dagger plus a hat minus a hat. The a dagger plus a hat is proportional to x hat. When that acts on x equals 0, it gives 0. That then replaces the a dagger with a minus a hat. Now the a hat can act on the 0 on the state on the right, and a hat annihilates the ground state, so that term is going to give 0. And I'm just left with this term, x square root of 2m omega 0 over h bar times that same overlap, x equals 0 acting on the ket 0. And so I just get that number that comes out. All right, and that's psi 1 of x. I hope that you recognize that those are the ground states and the first excited state of the simple harmonic oscillator up to a normalization factor that we still have to work out. But before we get there, we're going to work out the general case for all n. So I'm going to define a function that I'm going to call h sub n of square root of m omega 0 over h bar x. It's equal to square root of 2 to the n over this overlap, x equals 0 with ket 0, times the matrix element, x equals 0, a dagger plus x square root of 2m omega 0 over h bar raised to the nth power acting on ground state ket 0. These factors in the front, which look like they came out of nowhere, they did come out of nowhere. This is the operation that I call paying homage to dead French and German mathematicians. Those are the factors we need to use to relate these results to a mathematician named Hermite's work. Okay, now we just showed using this notation that h0 is equal to 1 and h1 is equal to 2 square root of m omega 0 over h bar times x. The fact that it's a 2 rather than square root of 2 is because of that extra square root of 2 factor that we put in when we defined the h sub n. All right, so the way that we're going to work this out is we're going to find a recurrence relation for general n. hn of square root of m omega 0 over h bar times x, that is equal to square root of 2 to the n, x equals 0, 0, bracket sandwich, and then I'm going to pull out one of the factors, a dagger plus x square root of 2m omega 0 over h bar, and I'm going to have n minus 1 factors left over. I'm going to now recognize that I can pull out the term that is a number, and that's going to be multiplied by hn minus 1, and there's an extra factor of square root of 2 that I have in there, so that's going to combine with the square root of 2 in the number and give me 2x square root of m omega 0 over h bar times that hn minus 1. That a dagger, remember, a dagger acting on x equals 0, I can replace by minus a hat acting on x equals 0. And then the a hat times this monomial raised to the n minus 1 power acting on 0, I can replace that by the commutator, because in the second term in the commutator, I'm just adding 0 because that has an a hat acting on the state 0 from the commutator. And the state a hat acting on 0 is just equal to 0. So I can replace a hat times that monomial raised to the n minus first power acting on the state 0 by the commutator of a with that monomial raised to the n minus first power acting on the state 0. Now that commutator is easy to work out. You have seen these kind of things before. The a operator acts like a derivative. It gives me an n minus 1 in front, and I get the monomial raised to the n minus 2 power. And you can see that that's going to be related to hn minus 2. I have to carefully work with all of the numbers. I find there's an extra factor of 2 that comes out. And when all the dust cells, there's also a minus sign there. You see I've gotten this recursion relation. hn is equal to 2 square root of m omega 0 over h bar x hn minus 1 minus 2 times n minus 1 hn minus 2. That turns out to be Hermite's recursion relation for the so-called Hermite polynomials, and h0 and h1 already agree with what Hermite called the 0th and first polynomial. And so we find that all of these this function hn of square root of m omega 0 of h bar x is just a Hermite polynomial. And using the physicist convention, those Hermite polynomials are written out for you in this table. You can go take a look at that carefully if you would like to. I just want to caution you that if you just randomly look up on the website or look up in some books, what are the Hermite polynomials, you have to make sure that you're using the physicist convention, not the mathematician convention. All right, the last thing we need to do is normalization. Now, no, the normalization only comes from normalizing the ground state wave function because it's this number, x equals 0, 0. That bracket sandwich is what we need. So we just plug in what is size 0 of x. We modulus square that. It's a real number, so it's really just the square of that. We take the integral over all x, and that should equal 1. Now, the integral of a Gaussian is easy to work out. It becomes square root of pi h bar over m omega 0. It's, of course, multiplied by this number that is left, modulus squared. I can solve for that number by dividing by the square root of pi h bar over m omega 0, taking the square root of that, and then saying that I want my ground state wave function to be real. So I'm going to pick the global phase for the wave function to be 1. Then we find that x equals 0 overlapped with the ket 0 is equal to m omega 0 over h bar pi raised to the 1/4 power. Now you see, everything we did in this derivation was algebraic. It all came from operators. In fact, it really all came from the fact that the commutator of x with p was equal to I h bar. Nothing else. No series solutions, no differential equations, nothing like that. I hope you find that this is pretty cool. Now, this is a really very recent result. This is work from the undergraduate thesis work of Mike Rushka, who was a senior in the college who just graduated last year. All right, now let's end by examining uncertainty. This is something that you have probably seen before, so I'm going to go through it fairly quickly. Again, I want to remind you what x hat is. Uncertainty, which I'm going to call delta x quantity sub n squared. The n indicates the state that I'm measuring it in. Delta x is the operator, and the square is because I'm looking at the squared uncertainty here. It's the expectation value of x squared minus the expectation value of x quantity squared. I just plug in what x is. I'll get some numbers out in front, a plus a dagger squared, and then some numbers times a plus a dagger quantity squared. I'm going to now substitute in what the state n's are. The bra is ground state a to the n over square root of n factorial, and the ket is a dagger to the n divided by square root of n factorial times the ket 0. And we plug that into both terms, the term with the a plus a dagger squared and the term with the a plus a dagger. Now we can immediately recognize that the term with the a plus a dagger is equal to 0, because the only way that that bra ket is equal to 0 is non-zero is if I have the same number of a operators on the left and a dagger operators on the right. But because I have an odd number of a dagger operators and an even number of a, or vice versa, we can never pair all a's with a daggers, and that result is equal to 0. If you don't immediately see that, think very carefully about how that works. Think very carefully about how you would do the pairing, and pause the video and make sure that you understand that. Now for the second term, we have, if I expand that square and make sure that I don't change the order, I have to maintain the order when I expand the square. So I'm going to FOIL it out. I'll get an a squared plus an a dagger plus an a dagger a plus an a dagger squared. Now the a squared has the same problem. I don't have as many a's on the left as I have a daggers on the right, so that's equal to 0. Similarly with the a dagger squared, the term a dagger a I'm going to rewrite as a dagger plus the commutator of a dagger with a, so that's just a dagger minus 1. And you can see the a dagger term, that's going to look like the state n, and when I work out the normalization constant, it's 2 times n plus 1 factorial minus n factorial. Okay? Now, we can fairly easily work that out. You see that I'm going to be dividing the whole thing by n factorial, so it's really 2 times n plus 1 minus 1, and that's just equal to 2n plus 1. So that's what I get for the uncertainty. I have the numbers out in front that we were carrying along, h bar over 2m omega 0, and it's times 2n plus 1. Now, you can do a similar thing with the momentum. I'm not going to carefully read out everything for you. The derivation is really quite straightforward. The only thing that is changing is a minus sign in the middle. Okay, so the average of p is still 0, and the average of p squared looks exactly the same, except there's a change of sign. But when all the dust settles after that change of sign, because there's a minus sign out in front, you find that it is equal to h bar m omega 0 over 2 times 2n plus 1. Okay, now if I look at the product, so I have to now take the square root of both of those and look at the product of them, you find it's equal to h bar over 2 times 2n plus 1. Now we know, you should know, that the minimal uncertainty relation is that the uncertainty in x times the uncertainty in p is equal to h bar over 2. And from this, you can immediately read off that the uncertainty is minimal for the ground state. And as I look at higher and higher excited states, that uncertainty simply grows. Okay, this has been a lot, but it's also something that you should be fairly familiar with, even though I have gone over it in a way that I'm sure is quite different from the way that you've seen it before. But with this work right here, we are now finished with Lecture 3 of Physics 506.